So in this lecture, we're going to introduce the concept of flux and how surface integrals come from that idea. So let's suppose we have a fluid, and let's suppose this fluid is flowing with velocity given by the vector field v of x, y, z. And let's measure this in meters per second. So at the point x, y, z, our velocity of our fluid is v, x, y, z. So what we're going to say is we're going to consider that we have a surface S that's immersed in the fluid. So one idea you could think of here is suppose we have blood flowing through a blood vessel, and then we put an imaginary surface inside the blood vessel, and we want to ask how much blood flows through that surface per unit time. So that's what we want to calculate. So we want to calculate the volume of fluid that flows through the surface per unit time. So this should be measured in meters cubed per second. So it's some volume per second. So we refer to this as the flux of our vector field V through S. Okay, so like I said, we can think of blood flowing through a blood vessel. So let's start off by looking at the simplest possible case we can have here. So let's suppose we have our surface here is S. And let's suppose our fluid is flowing and the vector field is actually constant and perpendicular to this. So V of x, y, z is constant and perpendicular to S. And notice I'm taking S here to just be a flat surface that we can find the area of, say. So simplest possible situation we can have. So let's ask what is the flux of this through here? So if we take our surface here and we think of water flowing through this. So think of the water that is right there at the time we start. How far will that little piece of water flow? So if I have some water here, and we know it's moving in this direction, we know that distance equals rate times time. And our rate here is the magnitude of v, which is just a constant. So if we flow for 1 second, this is going to go a distance of absolute value of v. So that will be down here now. That little piece of water will be down here, a distance of magnitude of v. But of course, all the stuff that was before that will also move through a different distance, so that the stuff that was back here, say if we take water that was back here, this is going to move somewhere into here now. So if we look at how much water has actually flowed through our surface in this time, well, the distance there is magnitude of v. So this region has volume, well, it's magnitude of v, and then the area of that surface. And notice this actually matches up even units-wise, because if we say flux here, well, we just said this should be magnitude of v area. Well, the units here, the units of v is meters per second, and the units of area is meters squared. So this is meters cubed per second. So the units match up just like we would expect them to as well. So that's the easiest possible case we could have. Now, one thing we want to talk about before we go any further is the orientation of a surface. And we're going to be a little loose with our definition here. Basically, we say a surface is orientable if we can choose unit vectors that vary continuously across the surface. So if I pick this to be my unit vector, unit normal vector here, then as I move it to a close piece nearby, these vectors all vary continuously. So all the surfaces we're going to talk about are orientable, and we'll always choose an orientation. Now, not all surfaces are orientable, so if you're familiar with a Mobius strip, that is not orientable. So for us, it's always going to be just choosing unit normal vectors that kind of go, all those unit normal vectors kind of go in the same direction. So let's look at a little bit more complicated version of our flux now. So let's still assume that V is constant. So we're not going to let V vary just yet, but let's not assume it's let's not require it to be perpendicular anymore. So let's suppose I have my surface S now. So let's make it a rectangle now. Doesn't really matter for what we're doing, but this is my surface S. And now say my fluid is flowing through this way. It's not perpendicular anymore. It's going at a bit of a diagonal through. So we can still ask, well, how much would flow through in 1 second? So same idea. Let's take our surface again. And now instead of creating just a box out, it's kind of going to the side here. So maybe let's say it's going something like this. And so this is how much this is the volume of the region that has flowed through now. And our unit normal here maybe looks like this. So it's not, this is our n hat here. And we're still assuming the surface is nice and flat, so that we'll take this unit normal to be just constant everywhere. So what we want is, what is the volume of this box? Well, in this case, we can think of this vector, our vector v, this blue vector, we can think of this going like this. This is my vector v. And so if we think of what the geometry is giving us here, we have a box that looks something like this, say. And if we think of our unit normal vector is going like this, and our vector v is going like this, notice if we take the projection of v onto n, that's exactly the height of the box. So projection of v onto n hat is the height of the box. So, well, the magnitude of this, of course, we need a number. So if we recall how to calculate that, remember the projection of v onto n hat is v dot n hat over n hat dot n hat n hat. So if I take the magnitude of this and I use that n hat is a unit vector everywhere, this just becomes absolute value of v dot n hat. So that's the height there. So the volume of the box is, well, we need the area of the base, and then we need to multiply it by the height. And note, we can go ahead, if we wanted to, we can bring that a inside, and we could write this as v dot a n hat. And often we'll write this a n hat as just a vector a. And in that case, we see the volume is v dot a. And so that gives me the volume of this box. The only thing we want to be a little careful with here is we assumed that our orientation when we chose this n hat is going in the same direction as v. And that isn't necessarily the case. So we could have a negative flux where things are going in the opposite direction. So our flux has to take into account the sign. So we really want just v dot a, which is v dot a n hat. Okay, and so that allows for it to be negative as well. So those are two simple cases, but those build into the general case. So now let's look at the general case. So now I'm going to do what we often do in calculus, and I'm going to say, take my surface and break it up into a bunch of little pieces. So I have my big surface here, S, and I'm going to take a smaller piece of this. So this is some little delta S here. And I'm still going to have I'm going to have a unit normal here, but now this unit normal is going to vary with x, y, and z. And I'm going to have my velocity vector here that also varies with x, y, z. So we're going to take those pieces to be very, very small. And let's set a vector here, a vector delta S to be the surface area here of this little piece times n hat at x, y, z, where we're choosing some x, y, z. This is all an approximation, and of course we'll take limits how we always do. So if we do that, then the flux through this little piece, so say delta flux, so flux through our little piece, well, this is going to be approximately, well, this is my scaled unit normal vector, so this is kind of my a bar here. So this is going to be delta S n hat of x, y, z dotted with my velocity vector there, which we can also write, of course the order doesn't matter here. We can also write this as the delta S. So that gives me my approximation for my flux through that little tiny piece of surface. So of course, to get the total flux, we want to add all those up. So my flux total is going to be approximately the sum, say, of all the little pieces. So we're not going to be super rigorous here with this. We're just trying to get an idea of what's going on. We've broken it up into a bunch of small pieces. We're going to add these up over all these small pieces. So I guess this should have an x, y, z with it because it does depend upon where we're at. And then, of course, just like we always do, to get the exact flux, we'll just take the limit. This is the limit, say, as these pieces of surface area get infinitely small, and we're still going to just loosely say add up over all the little pieces of v x, y, z dot this delta S of x, y, z. And so this is how we're going to define our flux integral. So our integral over S of v, and we'll write it as dot ds, is exactly this limit. All the little pieces of v. I'm going to write it with the n here, and then a delta S. So this is the definition of the integral on the left. Just like always, this is how we come up with the integrals. Obviously, this is not really how we want to evaluate them. So in some cases, this is going to work out just fine, but in a lot of cases, we're going to need a different method for evaluating this. And of course, this works for any vector field. It doesn't have to be fluid flowing. So in general, we'll just have the flux of F through S as F dot ds is just going to be this limit. Limit as delta S goes to 0 of the sum of F of x, y, z dotted with the unit normal at the point, delta S. So that's how we define the integral. So this is our definition. So let's go ahead and calculate an example that we can actually do with just the definition. So a lot of times we won't be able to just use the definition. We're going to have to parameterize just like we had to parameterize for line integrals. But sometimes everything works out nicely, and it's important to take advantage when those situations arise. So let's consider the vector field. Say f of x, y, z is equal to minus yi plus xj over x squared plus y squared. So remember, this is our vector field that's a rotational vector field. So if we want to quickly draw the picture of this, in the xy plane, remember this vector field looks like this. And then, of course, in 3 space, we're not taking into account z in our vector field, so there would just be these things stacked on top of each other, going up and down. So let's consider our surface now. So let's let S be the surface given by, you say S is all of the x, and I want y to always be 0, and z, and so this is going to be 1 less than or equal to x less than or equal to 3, then 0 less than or equal to z less than or equal to 2. So if we were to graph this surface in 3 space here, x, y, and z, this just looks something. We go over here, we go between 1 and 3 and up to 0 and 2. This is my surface S. And let's go ahead and give this orientation. So my n hat, since this is a flat surface, these are always just going to be constant n hats, and let's just call that j. So that's a normal vector going in the direction of y. So that works just fine for our orientation. So now if we think about the terms in our integral, if we go back up here and look at what we have, well, I just told you that n hat is equal to j. My delta s here, since this is a flat surface, delta s is just going to be a little change in x and a little change in z. So if I think of delta s as a vector, this is just delta x, delta z, j hat. And now we need to evaluate f on, so f on s is given by, well, to be a point on S, it should be x, 0, z. And if we do that, that just gives me x over x squared j hat, so 1 over x j hat. Because our y is 0 here, so that gets rid of part of the vector field. So on a small patch of surface, our flux is approximately, well, it's f of x0z dotted with this delta s is a vector, and so this is 1 over x j hat dotted with delta x delta z j hat. So this is just 1 over x delta z. So now if we want to do this for the whole surface, so our total flux here is then, remember this is given by this integral, this is the limit as delta s goes to 0 of the sum over little pieces of f dot, let's say f of x 0 z in this case, dotted with j because that's my unit normal. And so we can rewrite this because of how our delta s is defined as delta x and delta z go to 0. over the sum over all the little pieces of, and then we just had 1 over x, delta z when we carried out that computation. So notice this piece here is just a double integral over r of 1 over x dA, where r is the region. We can just think of this as just in the xz planes. These are x and z, so that 1 is less than or equal to x is less than or equal to 3, and 0 is less than or equal to z is less than or equal to 2. And now we know how to do an integral like this. These are the two-dimensional integrals we've already been doing. So we can just choose whichever order we want because this is over a nice box, so easy integral. And so this is 0 to 2, and then I get natural log of 2 minus natural log of 1, which dz, which is just then, oh, it's going from, yeah, so sorry, it should be a 3 here. So it should be then 2 natural log of 3. So we see in that case we can actually calculate the integral, that flux integral there, but it only worked out nicely because of how the vector field, notice the vector field was going exactly in the direction, since it was spinning around in this case, it was going exactly in the direction of the unit normal of s. So those came back to our very first situation where everything worked out quite nicely. Even our vector field wasn't constant, it worked out very nicely so we could answer that. So that's not always going to be the case though. So what we're going to need to do is the same thing we did when we were trying to evaluate line integrals, and we're going to have to parameterize our surfaces, which we've seen how to do, and then we're going to use those parameterizations to figure out how to actually evaluate the integrals with parameterized surfaces. So let's refresh our memory with a couple of parameterized surfaces. So let's just recall that to parameterize a surface, we need 2 variables because we have a 2-dimensional object. So what our parameterized surface will look like is we'll usually use the variables u and v, and so it'll be some function x of u and vi plus y of u and vj plus z of u and vk. And we're going to stick to pretty easy surfaces to parameterize for this. Obviously, it can get a little more complicated than what we'll do, but we're going to just stick to the main idea here is to understand flux integrals. So let's do a couple examples of parameterized surfaces just to refresh our memory. So let's consider the surface. Let's just take S to just be this square in the xy plane. So if we think of what this is looking like, this is just a simple square, but we want to, the idea here is we want to parameterize this in the form of RUV. So this goes up to 2, this goes out to 1, and this is our surface S. So in this case, this is not so difficult to do, so we can just take R of U and V. Now the easiest variable is we know Z should always be 0, so we can start with that. And then we can just take U to be our X and V to be our J, and then our region that we're looking at is just S. But we'll write it with U and V variables instead. So this is, so minus 1 is less than or equal to U, and minus 2 is less than or equal to V is less than or equal to 2. So that's one example. The most common example that we're going to encounter is actually one of the easiest to parameterize. So if our surface is given by z is equal to f of xy, so if we can write one of the variables as a function of the other two, we can always parameterize this. So for, let's say for xy in some region R, we can parameterize this as, well, let's just take u to be x, v to be y, and then z is just f of uv, k, for uv now in our region R. So that's the easiest one to parameterize, and we'll encounter that one quite a bit. And so we'll see some other surfaces as we go as well, but that's just a quick refresher on parameterizing surfaces. So now let's use these parameterizations to figure out a nice way to calculate our flux integrals. So let's suppose we have parameterized our surface. So it's given by some r of uv for u and v in some region R that's in the UV plane. Okay, let's also suppose we have chosen an orientation. Okay, so we've decided which ways our unit normal vectors are going to be going. So in other words, we have at each point x, y, z on the surface, we've chosen a unit normal vector. Okay, so now let's figure out how we're going to actually calculate this flux. So let's suppose once again we take a small piece of our surface. So let's say this is a small piece of the surface. And let's suppose this is given by some vectors. Since we have a parameterization, we have vectors giving this surface. So let's say this is r of uv, and then this is a vector. We just change, since this is a small slice, we'll just change this a little bit in the u direction, and then we'll have one going back here as well to this edge, and this is r of u v plus delta v. Okay. And so we have this these vectors here, and we know that we can take the tips of these vectors. Let me use a different color for that. We can form these vectors here, and this vector is given by r of u plus delta u v minus r of uv. And similarly here we have a vector going this way, and this vector is r of u v plus delta v minus r of uv. And so then these vectors here, these form a parallelogram like that. They're in blue. And so we know that's not that parallelogram isn't exactly the little piece of surface, but if delta u and delta v are small, then it's a pretty good approximation for it. So we have that blue parallelogram. The area of that's going to approximate the area of the green surface there. And we know how to find that area. So the area of the parallelogram, we think back to what we did with cross products. This is the magnitude of r of u plus delta u v minus r of uv crossed with r of u v plus delta v minus r of uv magnitude. So that gives us a good approximation for that for the surface area there. This obviously isn't the best way to calculate this. So if we look at each of these terms, we can see they look something like a partial derivative. So we would have r of u at uv. This is approximately r of u plus delta uv minus r of uv over delta u, right? Because the partial derivative would be just taking that limit as delta u goes to 0. And similarly for the delta v, so if we multiply both sides by delta u, I have r of u plus delta u v minus r of uv is approximately r of u uv delta u. And similarly, the same argument, if I use the v's instead, I get r of v uv delta v. So that means my little piece of surface area, so our little delta S, which is approximately the area of the parallelogram, which is approximately the magnitude of r of u uv delta u cross r of v uv delta v. And we can factor that delta u and delta v out, and so this is the magnitude of r of u uv cross r of v uv delta u delta v. So that gives us our little slice of area there. So that will replace our delta S in our approximation. So the next thing we need is our unit normal. Well, we can see that from the picture as well. If I take the cross product of these two vectors, the blue vector spanning this, that'll give me a normal vector to the parallelogram. And also the surface at that corner, since they're the vectors coming off that surface there. So our unit normal, n hat of x, y, z, is going to be r of u uv cross r of v uv, and then we want to make it a unit normal, so we have to scale it by its magnitude. And don't forget, we have the so we have the absolute values here on this because we need to scale it. Now the only thing to be careful of here is this r of u cross r of v might be going in the wrong direction, so really it's going to be plus or minus here, and we have to check which it is when we do the calculation. So we'll see this in the examples. It might be that you actually have to take r of v cross r of u to get the correct unit normal to agree with the orientation we've already chosen. But now if we combine these things, so our delta S, if we think of this as the vector, so this is of course delta S n hat of x, y, z, what we just calculated was, well, the delta S was the magnitude of ru uv cross r of v uv delta u delta v, and then I have for the, we're just going to ignore the sign here for a minute. So our unit normal vector is given by this. And so those magnitudes cancel out, and we get that this delta S is really r of u uv cross r of v uv. Again, we have to make sure the sign's correct, otherwise we change the order. And then we have this. So our flux through the little piece, through our little slice, is going to be approximately f of r of uv. So we have to look at it with the parameterization, and then we dot that with this unit, with this the vector delta s, delta u, delta v. And so now if we add all of these up and take the limits, we get that the flux, which was the integral over s of f dot ds, now in terms of our parameterization, this is going to be the integral over r of f of r of uv dotted with r of u uv cross r of v uv, and then we can put delta, or we'll put dA here, but it's the dA that goes with the region R. So this dA could be delta U delta, or dV du dV, or dV du, or maybe polar, depending on how we're going to choose our region. And it'll depend upon what the surface looks like and how we parameterize, which is the best way to do this. So let's go ahead and work some examples now to see how we can use this parameterization. And these examples are quite a bit of work. These flux integrals are not necessarily super easy. and they take a lot of steps, but they do. It's nice that they use a lot of what we have already learned in the course, kind of bring it all together. As we saw in that derivation, we use cross products, we use areas of parallelograms, we use vectors, all kinds of good stuff going on there. Okay, so let's take this vector field here, and we want this to go through the surface S. So this is going to be part of the cone given by z is equal to square root of x squared plus y squared below the plane z equals 1. And I want to orient this downwards. So usually when we say downwards or upwards, it's with respect to the z variable. So let's go ahead and draw a picture of our surface here. So our surface looks something like this. It's this cone. And I guess there's nothing. It stops up here at z equals 1. That's the top of it. And it's this surface here. It doesn't have a cap on it. It's just the cone. And since our unit normals want to point downwards, they should be the ones going like this everywhere. So you can see they should have negative z component. So whatever goes in front of the k should be negative. Now our first step here is to parameterize the surface. And so parameterizing the surface has nothing to do with the vector field. It's all completely based upon the surface. And in this case, we have the function z is equal to f of xy. So this is one of our easy parameterizations to do. So we can just take r of uv to be ui plus vj plus zk. So x squared plus y squared to the 1/2 k. And then we want to say, well, what are our region for this, for the u and v to get this entire surface? So if we think of maybe projecting this down to see what u and v we need, since we're just taking u to be x and v to be y, it would be this region down here would give us all of this, and this sits below this very top part when z is equal to 1. So when z is equal to 1, our kind of edge there is 1 is equal to square root of x squared plus y squared. That's our top curve there, the top of the cone, which is the same as x squared plus y squared equals 1. So we want our region R to be all of the u and v so that u squared plus v squared is less than or equal to 1. So just that circle there, or that disk, is what we want. And now that we have our parameterization, we can look at r of u, which is just going to be I. Oh, this should be u's here, not u's and v's there. Sorry about that. U squared plus v squared. There we go. And so then this should be 1/2 u squared plus v squared to the minus 1/2 times 2uk. And if we simplify this, this is I plus u over u squared plus v squared to the 1/2 k. And similarly, if we take RV, we're going to get j plus v over u squared plus v squared to the 1/2 k. And now we need to take the cross product of these. I'm going to have a 1, a 0, and then a u over u squared plus v squared to the 1/2, and a 0, a 1, and a v over u squared plus v squared to the 1/2. And so this is going to give me a negative u over u squared plus v squared to the 1/2 I. Then I'm going to get a minus v over u squared plus v squared to the 1/2 j, and then plus k. And now this is where we go back and we asked, is this the correct orientation? Well, notice the coefficient of k is positive, so this is going to be pointing up. We also see the coefficient of I and j's are both negative, so that's going to be pointing back towards the axis, the z-axis, And so this is the negative of what we want. So we want to match our orientation, we want r of v cross r of u, which is just the negative of this vector. So that needs to be our unit normal, or our normal vector, not unit, but normal vector. So the last thing we need to do here is we need to evaluate our f here on our parameterization. So we need f of r of uv. And so this is just going to be ui plus bj plus, and then I have the u squared plus v squared to the 1/2, and then that's raised to the 4th because that's our definition of f. So this is ui plus bj plus u squared plus v squared squared k. Now we can take the dot product. So I like to do all these calculations separately before I put them in the integral. Saves a little bit of writing. So we don't have to write the integral over and over again as we're doing the calculation. So this becomes u squared over u squared plus v squared to the 1/2 plus v squared over u squared plus v squared to the 1/2. And then minus u squared plus v squared squared. And we can simplify this a little bit because we can bring this first term together and get a u squared plus v squared over u squared plus v squared to the 1/2 minus u squared plus v squared squared. And that just becomes u squared plus v squared to the 1/2 minus u squared plus v squared squared. So now we have everything we need to set up our integral. And so my flux then is the integral over s of f dot ds. And this is the integral over r of u squared plus v squared to the 1/2 minus u squared plus v squared squared dA. And now this should be pretty clear. Our region we wanted to integrate over, if we look back up here, was a disk of radius 1. And we have a bunch of u squared plus v squareds here. So this is going to be best to be put this in polar coordinates. So then our limits go from 0 to 1 and 0 to 2 pi. And then I get r squared to the 1/2 minus r squared squared r dr d theta. And now this is a nice easy polar integral, the type we've already seen. So if I take r squared to the 1/2, I get r, but I distribute that other r through and I get an r squared. The second term here becomes r to the 4th, but then I have to multiply by r, so I get r to the 5th, dr d theta. This becomes 0 to 2 pi, and I have 1/3 r cubed minus 1/6 r to the 6th, evaluated from 0 to 1. So this becomes 1/3 minus 1/6 d theta. So this becomes 2 pi 1/3 minus 1/6, which is just pi over 3. So there's our first flux integral. So you can see these are that was a fairly simple surface and a fairly simple vector field, and it still took quite a bit of work to do. So that's how the flux integrals are going to be. They're always going to be quite a bit of work to do. Sometimes we'll be able to find some tricks where we don't have to do the parameterizations. And that's what we're going to see in the next couple of examples. So the next example is going to be a little bit more involved, but we'll also see later when we do divergence theorem an easier way to do this example. But the nice thing about this example is it shows us how we can combine parameterizations and also just using the definition to get a calculation done. So let's calculate the following. So we're going to do this flux integral f dot ds, where in this case our f, this is just going to be yj minus zk, and s consists of the paraboloid y equals x squared plus z squared for 0 less than or equal to y less than or equal to 1, and the disk x squared plus z squared is less than or equal to 1, and y is equal to 1. And this is we're going to give this with outward orientation. So this is a closed surface, so outward makes sense. So let's go ahead and start by graphing what this thing looks like. So we're going to do our coordinate axes a little different than normal here. So we're going to make this the y-axis because the paraboloid's opening in that direction just makes it a little more how we're used to drawing it. So that would put x here and z here. And so our paraboloid is going to look, it opens up like this, goes up to y is equal to 1, and then we have the surface on the top and the surface on the sides. And since we're going outward, our normal vectors look like this. So this is our surface S overall, but let's call the top surface S1 and the side surface S2. So if we do that, we can see if I want the flux integral of f ds, I can do this by calculating each one of these separately, which is really the way we're going to have to do this if we want to calculate this directly, because we can't parameterize both of those surfaces like that. So let's start by calculating the flux integral on S1. Now we could do this by parameterizing S1, and that would work perfectly fine. But we can also notice that on S1, our normal vector everywhere on S1, we can just take that to be the vector j, because it's just pointing straight along the y-axis. And if I look at f of x, y, z, well, on S1, I know that y is always equal to 1. So in that case, I can just take the values there are always going to be equal to 1. So this is x, 1z, and so this is just j minus zk. So if I dot those two together, and I dot this with this unit normal, well, you see when we dot these together, I just get 1. So when I look at this flux integral then of f dot ds, this is just the integral over S1 of 1 ds. And so this is just the area of S1. And in that case, we know this is a disk of radius 1. So this is just going to be pi times 1 squared, which is just pi. So that one was nice and easy to do. We didn't have to do any parameterizations. So let's move on to S2 now, which is going to require a parameterization. It's going to be a bit more work. So for this one, we'll start with since we have one of the variables is a function of the other two, we'll do our standard technique for this parameterization. And so in this case, now I want my u and v are going to be in that disk. Think of, we have to get this entire disk here to get that entire parabola. We're going to need this disk when we go down here like this. And we need all those values to get up to our parabola. So that means we want our u and v to be in this region R, where this is all uv's, so that u squared plus v squared is less than or equal to 1. And so now we can take our partial derivatives. So this is going to be I plus 2uj, and this is going to be 2vj plus k. And so now we need to take the cross product of these vectors. So I have I, J, K, and I have 1, 2U, 0, and 0, 2V1. So when I take the cross product of this, this is going to give me a 2UI minus J, and then plus 2VK. And so if we look at this, notice that the J component here is negative, which makes sense because for our orientation of the surface, we should be going towards the negative part of the y-axis. So this is the correct orientation. So we can stick with that one. And then we also need to evaluate our vector field on our parameterization. This is going to give me u squared plus v squared j minus vk. Now we can take the dot product of these two. And this is going to, so there's no I in the f component, so that will go away. So I'm going to get minus u squared minus v squared, and then I'm going to get a minus 2v squared. So this gives me minus u squared minus 3v squared. So putting that together, we see the flux integral over S2 is the integral over R of minus u squared minus 3v squared dA. And this seems like a pretty good integral to use polar coordinates on, so let's do that. So let's bring out a negative. And first we can write this as u squared plus v squared plus 2v squared dA. And then change this to polar coordinates. So I'm going to get an r squared plus 2r squared sine squared theta r dr d theta, where we're using v as r sine theta and u as r cosine theta. And so this becomes 0 to 2 pi, 0 to 1, and then I have an r cubed plus 2 r cubed sine squared theta dr d theta, which I can factor that r cubed. Comes out of both of those, and I get 1 plus 2 sine squared theta dr d theta. So integrating this first part, I get a minus 1/4 from the r to the third, and then 0 to 2 pi, 1 plus 2 sine squared theta d theta. And now we're going to use a trig identity here to do this integral. So 0 to 2 pi, let's leave that 1 alone, and then we're going to replace the sine squared with 1 minus cosine of 2 theta over 2 d theta. And so this becomes minus 1/4 integral from 0 to 2 pi of 1 plus 1 minus cosine of 2 theta d theta. So this becomes minus 1/4 integral from 0 to 2 pi, and then I get a 2 minus cosine of 2 theta d theta. And finally, this becomes minus 1/4, and I get 2 theta from 0 to 2 pi. And then I'm going to get a minus 1/2 sine of 2 theta from 0 to 2 pi. And so this just becomes, when we evaluate this out, I'm going to get a 4 pi, negative 4 pi there. So, and then the sine of 2 theta is 0 and 2 pi is 0, so I get negative pi for my final answer. So putting this whole thing together, we have f dot ds is, remember, the integral over s1 of f dot ds plus the integral over s2 of f dot ds. And remember, we calculated the first one as pi and the second one is minus pi, so the entire thing just gives me 0. So quite a bit of work to just get 0, but sometimes that's what happens. When we get to divergence theorem, we'll see a much, much faster way to do this. But for now, that's our method. So let's try one more example. So let's calculate the integral over s of f dot ds, where f of xyz is going to be xi plus yj plus 5k, and s is the boundary of the region enclosed by the cylinder x squared plus z squared equals 1, the plane y equals 0, and the plane x plus y equals 2, and we'll take outward orientation. Again, if you want an inward orientation, it's going to be the same calculation. You just place a negative. So that's our goal. So let's start maybe with a picture so we see what we're working with. So this one's a little bit messier to draw, so I'm going to start drawing it and then I'll put the axes in. So it's going to look something like this. So then we can put our axes in. And so this is going to be the y-axis, z-axis, and x-axis. So again, not the typical orientation for these, but this is how I chose to draw it. So the surface here is this top part, the side part, and then of course the bottom part. So the whole thing is S. Let's go ahead and give these some names. So let's let the bottom part here be S1, the side cylinder be S2, and the top one be S3. Because just like in the last example, we can break this flux integral over the entire surface into the flux integral over each one separately. So we got 3 calculations to do here. Okay, so now for the first one, let's start with S1. I'm going to start with the one that's going to be the least amount of work. So notice in this case, for outward orientation, our unit normal will be negative j, because it's going down, so it's going outward. And so if we look at our f here, f of xyz dotted with our unit normal is just y. But on S1, y is always 0. So on S1, we have f of xyz dotted with n hat of xyz is just 0. Well, obviously, if we integrate 0, we're just going to get 0. So our flux here is 0. So that's the easy one. Okay, so let's move on to S2, which we're going to parameterize. So let's take our parameterization. We're parameterizing the cylinder here. So let's use cosine of ui plus vj plus sine of uk. And here we want 0 less than or equal to 2 pi less than or equal to u. And now the v is a little bit trickier here. So if we think about this, when I'm going upward here in the v direction, I don't have a constant place I start. I start when y is 0. So I want to go 0 less than or equal to v, but now I want to go up to that cylinder there. Since I've let x be cosine of, remember it's x plus y is equal to 2 is our plane at the top, and we've let x here be cosine of u, so that we're going to go up to 2 minus cosine of u. Y is equal to 2 minus x. So our bounds are a little bit trickier here. So let's take r of u. So this is going to be minus sine of u I plus cosine of u k, and r of v is just going to be j. So if we take the cross product of these, I have minus sine u, 0, cosine u, and then 0, 1, 0. And if we work this out, this is minus cosine u I plus 0j, and then minus sine u k. And notice that's going to be the wrong orientation because those are pointing towards the origin. So we can see that by thinking, okay, well, if we take x equals 0, which would be when u is equal to 0, here, if we think of where any value here, this is going to be pointing in the x direction. If like u is 0, it's going to be pointing inward towards the y-axis. So we want the negative of this. So we want RV cross RU, which is cosine UI plus sine UK. And now we evaluate our vector field on this parameterization. And this is going to be cosine UI plus VJ plus 5K. So if I take the dot product, this is going to give me cosine squared U plus 5 sine U. There's no V component, or no J component in the RV cross RU, so that just goes away. So once again, I'm left with an integral with some trig functions in it. So remember, we're going from 0 to 2 minus cosine of U, and then 0 to 2 pi. And I have cosine squared U plus 5 sine U dv du. So pretty easy for the v integral because there's nothing there. So I'm going to just get a v with everything here. So when I evaluate that, I'm going to get cosine squared u times cosine of 2 minus cosine u plus 5 sine of u, 2 minus cosine u, all du. So if we simplify this out a bit, 0 to 2 pi, and we have 2 cosine squared u minus cosine cubed u plus 10 sine u minus 5 cosine u sine u du. Okay, and so now we've got a bit of work here. So we're going to use trig identities again. So this is going to become 1 plus cosine of 2u over 2. And then the second one I can write as cosine squared times cosine. So this gives me 1 minus sine squared times u times cosine of u, right? Because this is cosine squared u cosine u, and then you replace the cosine squared with the sine squared. And then the last two I can leave alone because those are integrals I can do. So let's continue to simplify this a bit. So I got 0 to 2 pi, and then I get 1 plus cosine of 2u, and then I get minus cosine of u plus sine squared u cosine of u plus 10 sine u minus 5 cosine u sine u du. And so if we evaluate these, we are going to get u from 0 to 2 pi plus 1/2 sine of 2u from 0 to 2 pi. And then I'm going to get, let's do one, so maybe let's leave those alone so that gets the first one. And then if I do the cosine, I'm going to get minus sine u from 0 to 2 pi. And then I'm going to get a plus 1/3 or minus 1/3. So we're going to use, so w is equal to sine u here. So then that will give me a plus 1/3 sine cubed u from 0 to 2 pi. And keep going, and then I've got minus 10 cosine u from 0 to 2 pi, and then a minus 5 halves. And if I use the sine, I'll get a sine squared u from 0 to 2 pi. And if you fill all of that in and work it out, this ends up just being 2 pi. So that gives me two of the surfaces. So far I had 0 on the first one and 2 pi on the second one. So let's go on for S3. Last one we need to do. So we're going to parameterize again. You can call the R something different if you like, but we don't really have to here. So we know on that surface, remember our surface is x plus y equals 2. So if I let x be u, then my y is going to be 2 minus u. And then I'll just let v be my k value. And what do we require here? Well, we want this to be inside the cylinder. So we want u squared plus v squared less than or equal to 1 for our region. Right? Because if we look back at our picture up here, it's this surface S3, but if x is u and z is v, then my u and v have to be inside the cylinder. X squared plus z squared equals 1. So this is our region. And now we just do the same thing we've been doing. So this just gives me I minus j. R of v is going to be just k. So if I take the cross product of these, this comes out to just be minus I minus j. And since we want outward orientation, this is again the wrong one. So we want RU cross RV, which is I plus j. This is outward normal. And let's evaluate our vector field on this parameterization. And we get ui plus 2 minus uj plus 5k. Again, we take the dot product. And this is going to give me u plus 2 minus u, which is just 2. And so this ends up being a nice, easy integral to do. I've just got f dot ds, and this is over that region R of 2 dA now. And since that region is just a circle of radius 1, this gives me 2 pi 1 squared, which is 2 pi. So now if we've done all of them, if we add all of these up, we have the first integral was 0, the second integral was 2 pi, the third integral was 2 pi. So we get 4 pi for our answer. And this is also a closed surface, so when we get to divergence theorem, we'll do this example again too and see how to do this much faster than breaking this up into 3 separate flux integrals and going through all of those.